Hi everyone. Can everyone hear me? Hear us on Zoom? Okay, perfect. We'll be starting in 1 to 2 minutes.
Okay, can people online hear us?
Yeah.
Yes.
Okay, sounds good. So welcome everyone to the I think the very last final review, and today we're going to talk about network, essentially how the internet works. Uh, let's see. Yeah, so the topics we're going to cover today, including like basically from the physical layer to the upper layers, from like MAC and IP, ARP, DHCP, layer 4, layer 5, until like the non-miscommunication like Tor. And we're going to go over each one of the item here like today. And so yeah, so today is mainly about it's like a mini lecture, so there will be no worksheet. And I think the idea is help you to like go over all these content and maybe help you to like make your own cheat sheet during the final exam. So some tips for networking. Do like networking topics are kind of like heavy, so it's like you really need a cheat sheet to include a lot of details that you can remember, and you need to understand the differences between like different types of attackers and like what's the capability of these attackers, and also thinking about like what part of message is like known by either the sender or the recipient. And also like again, since we're in the security, so we try to remember like what kind of values are public and what kind of values are secret. So we do have slide of cheat sheet. It kind of gives you like the high level idea of each protocol in each layer, but we're not going to spend time into this. If you want to like make this as a reference, you can. I think the slides will be public, and you just go and check those slides again. Yeah. So the first thing we're going to talk about is start with is like the basic physical layer. So the very first question is, let's say we have two computers in Soda Hall, and how can we connect them? So let's say we have two computers, Nick's and Raluca's computer within the Soda Hall. And how can we make Nick's computer talk to Raluca's computer in this case? So the solution is that we can just like connect these two devices with a wire, and we can write code that sends signals from one to another. So this is basically the physical layer, and it's basically we having a physical wire that can allows you to moving bytes around.
Slides are like cut off
Oh, wait.
because we're screen sharing to the projector or something.
Wait. Wait, so how can we solve this?
Give us a second, guys. We're trying to fix the slides being cut off.
Then, okay, we're trying to fix this. What should we do?
And just
Can you just share the desktop one?
this one?
Yeah.
Yeah, I think I fixed it.
Okay.
Yeah, perfect.
Okay.
Guys, let us know if it's fixed.
Yeah. So yeah, in the last slides we talked about when we have two devices in the same building, and then we can just connect them with the wire. But what happens when we have like more computers that needs to talk to each other? So one way is we just add a wire between each pair of them. So this kind of work if the organization is kind of small, let's say just three, but it wouldn't scale to like larger organization like Berkeley X. So instead of connecting all computers, like setting up like pairwise connection, we can just add a single wire and like let every single computer connect to this wire. And we can introduce a protocol to allow them to talk to each other in this case. And this is essentially the second layer, which is the link layer, and it connects machines in this local area network. So the gray box here is you can think of as the boundary of the line. It's a group of computers either in the same building, in the same institution, or some other like format. So now we need a way for these computers to talk to each other, right? So I think a common idea, like if you need to find one of these professors in this building, you do need to know their room number. So similarly, in the network, we have this idea called MAC address, and which is the unique identifier of like each computer in the local area network. So in this case, let's just think of like concretely the MAC address is a few like bytes of string, but now let's just consider it as like the room number in this other building. Yeah. So yeah, this is basically what I just mentioned, and it's unique within a building, but like different buildings may share the same room number. Let's say maybe in Corey, there's also this room called 625. Okay, now so what if Nick wants to send a message to Dave? And the idea is like Nick is gonna wrap its message into a packet which contains like a several like entries. So you need to specify the source, which is from room 625, and the destination is room 733, and also the payload contains the message, hi David. So this packet originates from this computer, and then because both Ralucas and David are connected to this wire, but both of them are going to receive this packet by just listening to this wire. And because Raluca will look at the destination field and see this is not a message for her, and she'll just like simply discard it. And for David, it's actually a message for him. So then David will accept packet and read the message. So the side note is that, so in the MAC address, we do reserve the destination of like FFFF to as a like reserved address, which means this message is a broadcast message that every single device that's connected to this wire should take this message. Yeah. So this is basically the Ethernet. And again, this is the layer 2, which is the link layer that connect all the machines in the local area network. So a quick summary, layer 1 is the physical layer that connects two machines together using a physical connection. And layer 2 is the link layer that allows you to have like two or more computers connected in this local area network to communicate to each other. And we use MAC address to uniquely identify each machines in local area network. And the MAC address is like, each MAC address is 6 bytes. And all messages are sent to all the other computers, but the computers only keep or process messages that the destination matches their own like MAC address. And Ethernet is just an example of like link layer framework. And we do have this MAC address alt F reserved for a broadcasting message. And in this case, all the message, they are like best effort. So there's no like guarantee that the packet will reach its destination. If you can think about, let's say, David's device is off when Nick wants to send the message. So in this case, David will miss the packet, and there's no way for David to recover this message because it's best effort. Yeah. Okay. So now if we think a bit more, let's say we have two buildings, Soda and Corey, because that's where like each department is at. And how can we connect to computers across these two buildings? So here's a slightly more complicated diagram. We have 3 computers on the top in the Soda hall. We have another 3 computers on the bottom in the Corey hall. And what happens if we want to connect to a local area network between them? So we can use a router to connect multiple LANs. And the way it works is like we're going to introduce another layer, which is the internet network layer, or like the layer that requires IP, which if you are more familiar with this notion. So basically this layer connects multiple local area network to form a wide area network. So let's say now Nick wants to send a message to Claire, and Claire is in this Corey hall. And we need a way to uniquely identify Nick's computer across the entire like internet, which is going to be the IP address. So now we have an IP address under each computer as well. So let's assume that Nick knows Claire's IP when he wants to send a message, and he actually can get this through DNS, but we're going to talk about this later. And now the original message will be like, the source is from Nick's IP, the destination is going to be Claire's IP, and then the payload is hi Claire. And then, but the only way that Nick know how to talk to Claire is over layer 2. So he wraps this layer 3 packet in a layer 2 packet, which is, remember that in layer 2, we use MAC address to identify the sender and recipient. So in this case, of course, the source is going to be room 625, which is Nick's location, and the destination is unclear. So yeah, so in this case, Nick doesn't know what should be the destination MAC address, but then this slide is a bit weird. Oh, yeah. And then we're gonna like get a short summary first before we get into like how can Nick, what's the protocol that Nick can use to resolve the MAC address for the recipient. So in layer 3, the internets are connected to layer 3 basically connects multiple like local area network through routers. And in layer 3, the identifier is is called IP address, and it's also unique for each computer in the network. And to send a packet using layer 3, we do need to like attach layer 2's headers on top of it and send the packet over layer 2. So the layer 2 is the headers that contains the MAC address, and layer 3 is the headers that contains like IP address. So now the missing part is that we don't know what to set for the destination part of the MAC address in this packet from NIC to clear. And yeah, so this is basically a protocol called Address Resolution Protocol, or ARP. So again, back to this diagram. Now we're missing this destination MAC address. And there are like multiple cases in ARP thinking about it. So if the target is just like within this like a local area network, they can simply just broadcast, okay, what is the MAC address of 129.0.3.18? So if you check the diagram, you can see that is actually like Rilke's IP address. And then when Rilke see this message, and she can simply respond with, okay, my MAC address is like room 729, and my IP address is like 129.0.3.1.18. And then once Nick receives this message, he can actually like send the packet and set the destination like MAC address to Rilke's like room number, which is 729. So now the case 2, which is the example we used at the very beginning, is Nick wants to actually send a message to like Claire. And he look at this like Claire's IP address and realize, okay, Claire might be outside of this local area network. And there's no way for Nick to directly like broadcast like message like he did in Rilke's case. So now instead he broadcasts like, hey router, what's your MAC address? I do need you to send a packet to need you to forward this packet to the internet. And then router will respond with the message, my MAC address is like something. So in this case, will be 129.0.3.1. And then Nick can remember this like IP address and then sets the destination to just router. Yeah. So in this case, this packet will be sent to the router first. And inside this, like the outside packet, like the layer 2 message will from the room 625 to router, and then inside of this header, this is going to be like the layer 3 packet, which contains the source destination IP and the payload. So a quick summary, ARP is a protocol that allows us to like use what we have already, like a layer 2 connection between devices in the LAN to translate the IP address into MAC address. So the protocol is like this. If Nick wants to send a packet to Rilke, which is in the same local area network, and Nick knows Rilke's IP address, it simply broadcasts a message containing what is the MAC address of 1.1.1.1. And once Rilke see this message, and she can just simply respond by sending a message only to Nick that my IP address is this and my MAC address is something else. And once Nick get this message, and he can actually like put this into his cache and then include this part of the information in the future packet. And if Nick's trying to find MAC address that's outside of the local area network, he can instead ask the gateway or router's MAC address, and router will receive this packet and forward to the next hop. And we're going to talk a bit more on this later. So the security of the ARP protocol, one big issue is called ARP spoofing. So when Nick requests Rilke's MAC address through ARP, actually anyone, because remember that in layer 2, everyone in the network can see this message and anyone can respond. So we don't have a way to actually verify like the packet is actually from Rilke or not. So let's say we have a malicious like user malware in this local area network, it can just simply run racist Rilke's response with a like forged response contain her own MAC address instead. So in this case, Nick will treat the Mallory's MAC address as Rilke's address and send all the future packet to Mallory instead of Rilke. And one technique to defend this is through switches. So traditionally, we just connect all the devices into a local area network to a hub, and then with switches we can just like connect all devices to a switch, and then the switch has a built-in MAC cache to track the IP address to the MAC address pairing when the IP address are first assigned. So in this case, when the malware try to like spoof the ARP request, it will be detected by the switch and the packet will be dropped. But actually, this is going to be like pretty expensive, and because we're kind of making the switch like we're kind of incorporating complicated logics into the switch. So it's going to be you do have more functionality, but it does come with like more computational costs. Okay, so let's go back to Nick and Claire case. So Nick now use ARP to figure out like where to send this packet to, which is basically the router or like you can think of it as the soda front desk if you think of actual mail instead of the internet. And this packet will then goes to the front desk, and the soda front desk will unwrap this MAC header and realize the packet needs to go to 129.0.4.20, which is basically a building inquiry. So in this case, it will like unwrap this part and wrap it with another header, which is where the destination is set to be the query front desk. And this layer 2 packet will then, actually, this packet will be like sent to the query front desk and be unwrapped, and the query front desk can see this like layer 2 packet again and realize that the destination is 129.0.4.20, and then it does know that this destination is actually to clear, and in this case, query front desk can just like use ARP again to figure out like what's the MAC address of clear, because now they're in the same local area network, and then wrap this message with the right destination, which is room 625, and broadcast to the entire like LAN. And finally, Claire sees this message and then accept this message because the destination is actually indeed the 625. Yeah, and finally, Claire can see this message. Okay, and the next part, we're going to talk about how do computers and Soda and Corey to get their IP address, which is the part we didn't mention in the previous story. And I'm going to hand over to Zoir.
One chat question. All right. Hi, everyone. Let's talk about some DHCP, which is essentially the protocol your devices use when they first join a network to be given some sort of like pieces of information they need to know about themselves to be able to talk to the internet. Okay, I think it will make sense once we go through it. So, is it? God. Okay, like this maybe. Okay, so we have our, again, same diagram, more or less. You have Nick's computer, you have Raluca's, Dave's computer, and then when Nick first connects to the network, he needs IP address, right? So how does he get to know his IP address? Well, this is where DHCP comes in. There's like a set of protocol that we use for Nick to be able to figure out like what its IP is. So let's go here. Okay, so first step is called client discover, and it's as the name says. Nick just says, "Hi, I need configuration." And this is for the routers to pick up and give some sort of answer, right? So step 2 is server offer. So any server who sees the discover says, wait, do I have configuration for this user or not? And then if they do, they give an offer. So the offer includes all the pieces of information that Nick needs. We'll go through the offer in a second. And then step 3 of this is, I guess, this is the information. So this is the 4 pieces of information that Nick receives from a server. And then step 3 is that you have client request. So each server needs to know if the offer was accepted or not. Usually we only have one server, but besides the point. And then Nick says, oh, I've chosen XYZ, for example. And Nick has to broadcast that again so that the server that offered the configuration knows to keep that connection alive. So step 4 is called server ACK, and this is the last step of the DHCP. And this is essentially server saying, okay, I saw that you accepted my offer, like I know. So Nick can safely use that configuration. All right, so quick summary. It's not a complicated per se protocol, but essentially it's used for layer 3, or it uses layer 3, and it's used for the IPs because you need to know the information. And when you first join the network, the router is your point of access to the internet. So you would want like the server to give you that piece of information. And the handshake is just 4 steps. So client says, hey, I need configuration. And a bunch of servers, if there are a bunch of servers, tell the client, hey, I can give you this configuration, right? And the client chooses one, and the client says, I've chosen configuration X. And so it broadcasts again, and then the server that offered X will take that in and says, oh, okay, the user Nick is using my configuration, right? Another important point, quite interesting, is that multiple computers can share a global IP using network address translation. And essentially, the idea is like you are within the network, 'cause since we're all local, right? We don't need unique global IPs. What that means is like when the router talks to the internet, the router can only have one IP address, right? It doesn't, and the users would that rely on the router can have whatever address, to be honest. It doesn't matter since they're talking to the internet through the router. So how network address translation works is that uh, it assigns like any IP to its users, and then when the user sends a packet to the internet, it changes the IP to be routers, but it uses something called logical ports, and that's essentially not physical but logical. So like user A would get a port like 50,000, for example, and then the the router changes the port to 50,000. So then when the packet comes back from the internet, the router can translate it back to be the specific user. Essentially, the big idea is that since you're talking through the router, that's the point of contact to the general internet. So we don't need each computer within the router to have a unique global IP, since there's way more computers than available IPs in the world. Okay, quick security slide. I guess this is important. So the DHCP spoofing is an attack that you can do on DHCP, and essentially it's like the NIC broadcasts a request, right, for configuration. And then Mallory tries to race the actual servers to offer a fake configuration to Nick. And so when Nick sees the configurations, it accepts Mallory's if she wins the race. And that means now every point of like sending packets goes through Nick, right? And obviously this is vulnerable since she becomes like man in the middle, she can do whatever she wants at that point. And the only real defense against this is just rely on higher levels, like we'll cover TLS to do end-to-end encryption. So then that secures the connection. But in terms of DHCP itself, since it's lower level, there's not much else we can do except make sure people in our local network are not someone malicious. Okay. Now, how do we build apps on top of IP? So if you send packets over layer 3, which is the internet or internetwork, it's all one time and only best effort only. So what that means is like we want some sort of notion of connection and we want reliability. Okay, so this is just if you open your activity on your Mac, for example, it just shows you all the connections on your computer, essentially, on the network. And then if you just look at the ports, this is the assigned ports your laptop gave to each of these applications. Okay, I think this example is probably better. So let's say Slack wants to open up a connection to the server, and we know the server is hosted at this IP and port 80. So the first thing is NicOS does, it says, let's do a TCP connection. And I'll give the Slack app a port number of 1234, let's say, the local app, right? And that's just a logical port we give to the next Slack app. And then this is the configuration at the beginning. So you have your source port, destination port, your sequence number, which is random. And then you have a flag, which I will cover in detail in a second, but that just says like SYN, which is like your first message you're sending to the server. And we wrap it up in a lower level, like layer 3, and then we send it over to the internet, right? And then the Slack app gets it in reverse order and it translates it down, and then just unpacks it and does whatever it needs to do. But the point is that we've tied this back to layer 3. And we're going to abstract that away for the rest of the sequence of events. Okay, I think it makes more sense if I just show TCP. All right. Okay. So we send this packet, or we want to send this packet, right? So the Slack receives this message, and what does Slack server do? It knows like, oh, okay, this user is trying to do TCP with me, so I'm going to generate a B, as you can see, the sequence number, which is also random, and it's usually 16 bits, and then it takes the sequence number that is also random from A and or like the A and does A plus 1 as the ACK. And the flags is like SYN ACK because it's you're acknowledging the SYN that the user sent you. And now Nick sends a packet with the ACK flag set, right? Which means like you got this in ACK. And then the sequence number is set to A plus 1 and the ACK is set to B plus 1, right? And that's the important part, that these two random numbers, A and B, are now being done plus 1, right? So if we carry on, this is the core idea of TCP. It relies on the fact that the client and the server both have like 16-bit random numbers, and each of them send that no random number plus 1, right? So for an attacker that's not there, I guess we'll cover in a second, but they essentially have to guess the entire number. Because if the ACK is not what you send plus 1, then you know that this is like a forged message, right? So the key idea is that these sequences are random and they have to be random for security, and they are shared through this handshake that we just went through. And again, one side receives TCP packet, it responds with an ACK specifying how much data was received by providing the index of the next piece of data that it expects. And after the handshake occurs, the client and server can communicate by sending packets to each other. Okay, quick summary of uh, TCP/UDP. If this is a bit fast, guys, the textbook is a very good visual examples too, so I recommend checking that out on the website. Okay, now the summary of transport layer. So we have TCP or UDP, like that delivers packets essentially between two machines, and UDP doesn't guarantee order of delivery or reliability. It's good for sending stuff very, very quickly since it's less processing time, and which you might see a lot of your streaming services using more UDP since they care about the volume of transmission, not the reliability. TCP ensures order and ensures reliability, and it does that by if the packet is dropped, then you never receive like an ACK for that packet, so the sender knows, oh wait, I need to resend that thing. So similar logic applies for the cake when ACK is dropped. Yeah, that's the same thing. So if either the packet or the ACK itself is dropped, we just resend. Each process is assigned a unique 16-bit port number by the OS. So you have IP and then you have port to uniquely identify one process on a machine. On client machine, for example, your laptop, the port numbers are arbitrary. And then on a server, they are usually well-defined and they're fixed. For example, like HTTP requests always go over 80, port 80, and HTTPS go over 443. This is needed because a lot of clients communicate to the server, so we should know which port we should be referring to every time. Okay, so this is like the packet that came from Nick's computer would look like. Obviously, each layer it wraps around that the higher layer, right? Since we have to wrap it around and then send it over through the link, which is the internet or the Ethernet, and then it goes to layer 3, which is the internet, and then layer 4, and then all the way up to the application on the server side. Okay, now the security of this layer. So something called TCP packet injection, and that's when the attacker spoofs a malicious packet, essentially just forging a packet, right? And this is very, very difficult for off-path adversary since they have to guess the IP and the port. And this is quite difficult, right? They have to guess it for 16 bits, which is to 16. And this is actually quite easy for on-path since they can just read the headers, right? But the only problem with that is that they are basically always racing because the real server also received these packets. So they just have to win the race every time to be the first. And man in the middle, this is kind of trivial because you're not even racing. All you have the entire flow through you and you can see everything. So you can just execute your attacks however you want. And now there's something called RST injection. And that's like RST is like a specific packet flag. For example, SYN, ACK, right? There's RST, which tells the server to end the connection. And you can think of it as like if you're watching like some stream and then the stream just casually ends your connection every time. And this is like why attackers would kind of use this potentially for censorship or what other reason to terminate the connection. And the defense is for both of these like TLS. However, RST is basically like it doesn't matter if you're using TLS or not, since RST is a lower level uh, attack. It relies on a lower level that doesn't use encryption. And so if RST happens, then it's like encryption doesn't protect you. So you just have to make sure you're using random numbers for those sequences. Okay, so how to make TCP secure? And this is when we build on top of the TCP and we use something called TLS.
There's a message. Okay. Yeah, so I think all the entire like TCP protocol we've seen so far is like in clean text. So it does allows the man in the middle to perform a bunch of attacks. And so the next thing we're going to talk about is how we use asymmetric encryption to make sure we can set up a secure channel between the two parties that gives you like both confidentiality and also the integrity. And that's essentially like transport layer security, which is TLS. So TLS provides an like end-to-end encrypted channel for communication. It's built on top of TCP. And a lot of connections like HTTPS, SMTP, or VPN, they're like connections that you build based on TLS. And messages in TLS have both integrity and confidentiality guarantee. And since we're using the asymmetric cryptography, we do need a way to track the public keys. So we do rely on the certificate authorities to prove us that whether a public key is valid or not. So the high-level idea we use, again, we begin with the standard TCP handshake, and then it's basically the browser sends a send to the server, and server responds with send ACK, and then there's a typical like TCP handshakes in 2 times. And something different with TLS is now the browser is going to send a client hello, which contains random number R, and also a list of encryption protocol that this browser supports. So when server sees this message, it will also respond with another random number, RS. You can think of these two as like the random source of this connection, and also a list of protocols that the server supports.
Oh, so protocol is in this case TLS, right?
Yeah, in this case TLS, but then also like you can also consider like you will see in the next round like what are the protocol you're going to use to generate the pre-shared like secret. Is either like RSA or like deep Hillman or like something else. But it might contain some other stuff too, because now the TLS is like we're talking about, I think TLS 1.2 or something, or 2.1 is like, but the actual TLS protocol we're using is like a level higher, so might be different. Yeah, so in server's response, there's also going to be a certificate, like we mentioned, that we do need to know that whether a server's public key is actually the server's public key, so that we kind of requires like a CA to help us verify that. So with these two messages, the client is first gonna go to verify the certificate, and if the client trusts the certificate authority and this authority did sign this certificate before, then client trusts the server, and then client can use this server's public key to set up the communication in the later rounds. Yeah. So the next step, since we're trying to set up a secret channel between these two parties, and we do need shared secret. So the goal for next step is to generate a random pre-master secret, then known only to the server and the client, and specific to this connection. And we have two ways to do this. One is through RSA or through like DB-Hillman key exchange. So the first approach, the browser can simply just generate this secret and encrypt the secret using like the server's public key. And once the server receives this ciphertext, it can just decrypt its own private key. And this is through like RSA, like the public key encryption. And the second approach is using DB-Hillman key exchange, where both sides can send the public part of their DB-Hillman pair, which is G to the A mod P and then G to the B mod P. And then after this, both parties will have the shared secret, which is G to the AB mod P. And yeah, this is essentially just the DB-Hillman key exchange protocol we mentioned in the crypto section. Okay, now we have the shared secret, and then we can derive the other like keys or things we need for encryption, integrity for the client and also the server. So remember that we do need encryption key for like specific to client and server. And I think there's a reason we do this, and I'll leave you to think about it. So once we have all the keys we have, the next thing is we're gonna verify the integrity of the dialog we sent before. So in this case, browser is gonna compute the MAC of the dialog it has seen so far with its like integrity key, and the server will do the same thing. And both sides can make sure that the entire transcript is aligned and nothing is being tampered. So once these are down, there is this secure channel between these two parties, and then they can like communicate using the encryption key, and also like they can make sure the integrity by using the like the MAC key. So a quick summary about TLS. So in TLS, we do have the guarantee that the client is talking to the legitimate server. This is done through like the client will verify the server's public key through the certificate authority. And nobody can tamper with the handshake because we do mark the entire dialogue after you generate this pure share secret. And these two parties share a set of secret keys, including encryption keys and integrity keys, that gives you the confidentiality and integrity of the message. And remember that using DB-Hellman key exchange provides you with the forward secrecy, but RSA does not, because if attacker discover the server's secret key at some point in the future, and he can just simply use the secret key to decrypt the pre-shared secret and then generate the encryption key and integrity key, and basically just can decrypt the entire like transcript. But if you're using DB-Hellman key exchange, then you don't have this issue. And TLS also provides against replay attacks, and because we do have some randomness sent from both parties that make the key like kind of unique across different sessions, so that you cannot really launch any replay attacks in this case. Yeah. Any questions on this part? I'll just pause like for 10 seconds. If you want to ask questions, you can feel free to like just speak or like type into the chat. Okay, so now we've talked about TLS. The next step is like we're going to cover something about the Wi-Fi, which is how does Wi-Fi work? So in Wi-Fi, there's one protocol we're going to use. It's called WPA-PSK. So essentially, Wi-Fi is the implementation of like a wireless implementation of the link layer, and it behaves similar to the Ethernet, but the difference is like everyone can actually see the access point, which is unlike the Ethernet, you actually need a cable that connect to your computer. And Wi-Fi is like everyone, you allow like the devices to join or leave this like this network, and therefore you do need like say the access point, which is you can think of it as like the device that sends out the Wi-Fi signal that I'm here like in a broadcast way. And for devices that want to join a particular network, you just simply broadcast the request. And WPA2 PSK is a protocol for like for each device to set up a secure communication with the access point. So the sanity check here is why don't we have a like equivalent communication over the Ethernet? And the threat model is different because for Ethernet, you do need the device to like plug in, which is like hard. But for Wi-Fi, it's slightly different, and everyone can see this message from access point, and everyone can try to like join this network without even have to like a cable connected. Okay. So let's say now Nick wants to connect to the Wi-Fi access point. So the configuration of this access point, including the SSID, you can think of just the name and also the password, which is the password you need when you actually connect to Wi-Fi. And the access point then will, based on this SSID and the password, derive a pre-shared secret. We're basically using this PBKDF to generate this pre-shared key. And then the access point is going to also broadcast this SSID to everyone nearby. So you can think of it when you open your settings on your phone, and you can see a list of like Wi-Fi that's available at your current location. Okay, now let's say Nick actually wants to connect to this Wi-Fi access point. Nick will like make a authentication request, and then both sides is going to generate the pre-shared secret key using PBKDF. So let's say on the Nick side, because we do require that you know the password to be able to connect to this Wi-Fi. So like this pre-shared secret key is going to base on both SSID and also the password. So and after you generate the secret key, both sides also going to send a nonce, like different nonce, just like the random value to each other. And then both sides are going to derive like a pairwise transport key that's specific to this session. So you can think of it like if Nick doesn't know what's the password for this Wi-Fi access point, and the pretty sure secret key will be different, and then essentially there's going to be you cannot set up a connection. Yes.
Why do we have two? Wait, so anons and s-nons
Yeah.
are both the same length, except like, so A is because it's coming from Nick or A key, or it's coming from A key.
Yeah.
But S is coming from, like, why is it named anons and s-nons? Just wondering.
Good question. Do you know that? Think of it as like some convention. Yeah, but the idea is just have randomness from the both side. Yeah. Yeah. Maybe it's S for a student. I don't know. Yeah. So yeah, so based on this like randomness and the pretty sure secret key, you can actually generate this pairwise transport key. And then both sides can also exchange the MAC over the exchange. So far, just remember it's similar to TLS that you do need to ensure the integrity of the dialogue so far because you don't have this pretty sure secret before. And then afterwards, the access point can just encrypt the group terminal key using the PD key that's generated as an encryption key and send it to Nick. And then these keys are going to be used for communication between the client and the access point. And that's the idea of the Wi-Fi protocol. Sorry, the WPA PSK protocol. So the security issue of this protocol, the first attack is GOG access point. So like anyone can actually pretend to be the access point and then offer the client an anons, but this only works if the attacker actually knows the PSK. So a second attack, which is I personally have tried like in the past, is like you can try to like brute force the password of the Wi-Fi because normally you don't have enough entropy in the Wi-Fi. For example, if you go back like 10 years ago, a lot of Wi-Fi passwords just 1, 2, 3, 4, 5, 6, 7, 8. And if you use that, you can actually break a lot of like Wi-Fi connection. And this works because the nonces are not encrypted and the MAC addresses are basically just public. And if you can guess correctly the Wi-Fi password, then you can connect. And the third attack is like no forward secrecy. Let's say if the attacker learns the anons and s-nons later and discovers the Wi-Fi password, and if they do have like a transcript of the past connection, they can actually derive the key and actually decrypt the entire like transcript. So the defense of these attacks is one thing you can do is called WPA Enterprise. Instead of using a like pre-shared secret key, it uses a one-time randomly generated key by the authentication server. And like in WPA Enterprise, like the username and password is kind of unique to every user. So think of it as the Azure one you're using now in Berkeley. Yeah. Yeah. And the next part is how are we going to find the IP address for domain? So by domain, we can think of it something like google.com. How do we know what's the IP address under this like Google's domain? Yeah. I'm going to hand it to you.
Right. Actually, pretty interesting section. We're going now into DNS. Okay, so DNS is domain name server, and this is essentially how like the general theme is like we use something called google.com, right? But our computers obviously don't speak English, so they need to translate that into an exact IP, and this is exactly why DNS is used. Okay, I think best way is to just show an example. So how do we find the IP address of, for example, x.berkeley.edu, right? From POV of Nick's computer. So we want to know the IP, and we go to something called dot or like the root server. And essentially on the internet, you have like root servers, which are the highest level of the tree, which we'll show in a second. And they are responsible for everything under dot. And everything is under dot, right? So we asked the root, like, hey, do you know the IP of x.berkeley.edu? And then the root says, like, I don't know exactly, but I have children with these domains. Go speak to them, right? So we have .com, .edu, and .org. And of course, we want .edu since our domain that we want is xberkeley.edu, right? So then once we get the IP of edu, we can make a request directly to the edu, which is the child server of root. And then we ask .edu, hey, do you know the IP of x.berkeley.edu? And then again, this edu has two children in this case, like Berkeley and MIT, right? And it says, I don't know the exact answer, but maybe talk to berkeley.edu, right? Oh, you mean the... Oh, okay, we're gonna go through this in a second. This is a type of record that the answer from a domain server comes back in. So it kind of jumps ahead a little bit, but it will make sense in a second after it says. Good question. Okay, this is a good question. And that's for berkeley.edu, and then you talk to Berkeley, and x.berkeley.edu is right under Berkeley, so Berkeley knows the IP, and then Berkeley says, here you go, take this IP, and then next computer takes these and caches them, right? And now going back to the original question, so this is what the DNS response looks like. For example, you can do this on your local computer too, if you want to try it out. And so what you have is your question. You have x.berkeley.edu. So this is our question. It contains usually only one question. And it says, I want to know the IP of this domain, right? Then we also have the query's ID, which is like a random 16 bits, since we're sending it over UDP. And that's DNS is over UDP, by the way. And then we have something called NS sections. And what NS is like a mapping, right? Between the domain and then it's like another name domain. For example, like we asked edu, right? And edu said, I don't know, but like the name server you can talk to, or like let's take it back. The root gave you edu servers to, like, if you go back here, like the root told you to contact edu, right? And so like the problem with this is that we have different types. So we can have like answer, which is the exact domain and the IP, right? But since we don't know the answer, we have to use something called a combination of name server type, NS, and answer. So what root gave you is like this is the edu server, and then the name of the domain of that server is called like a.eduservers.net, right? So this is like a stepping stone between these two. And then once you know it's like a.eduservers.net, what you can do is you need the actual IP to talk to it, right? And then you go to something called additional section, which contains the mapping of the IPs to that name. And the reason you see a bunch of these servers is because usually, obviously, we don't rely on one server. So like even for .edu domain server, you have multiple machines that all share the same thing, right? Just for like, if one breaks down, you don't want your DNS to fail. It's a bit of a confusing slide since they kind of like put everything onto you. But the general hierarchy, like idea of DNS is that you have something called root server, which is responsible for essentially everything. And then as you go further and further down the tree and you get more domains under it, each of the domains have like a responsibility, or like they know the children of their own domain, right? So edu knows Berkeley MIT, and Berkeley knows X might know something else, and so on and so on. So this is the summary. It's kind of the same thing. You talk to root. Root gives you like, hey, this is the child I have. Go talk to my child. You talk to the child, that gives you another one. And then you talk to the final layer, which actually knows the mapping of x.berkeley.edu, and that can give you your answer section. I think the slides, but do they have? Okay, they don't have like a good example, but what you would have here is you would have like, if you look to the answer, it says 0, right? So if it's the final layer, for example, berkeley.edu, you would have answer 1. And if you anytime you have answer, that means we've finished, right? So the answer would contain exact mapping. The answer would have x.berkeley.edu, and then you would have a type, and then you would have the actual IP. And this would be your final reply from berkeley.edu. Okay, so this is a summary of DNS. It's a protocol used to translate domains into IP addresses. And name servers contain mappings of domains to IP addresses for a specific set of domains. And the protocol is if you want to know the IP, for example, of x.berkeley, you contact the root, and root tells you it's child server. You can contact again, and then you go to contact edu, and then edu tells you berkeley.edu, and so on. And every time you receive responses, you can actually cache these to not go to the actual server every time. And when you cache these responses, they have something called TTL. And this TTL actually shows you how long you can keep this in cache. So like this number here, the 172,800, I think, is the TTL, and it's like I don't know how long that is in seconds, but like 40 hours. I don't know, but it's like some hours when you translate to seconds, and that means once you know the address of like edu and this is cached, you don't actually go to root. You just go exactly to this IP that you already know, right? Same thing for like any other DNS response you get. And this is why the security implications come in. Number one, the first attack is called spoofing or cache poisoning. And essentially, this is you return a false IP domain mapping. And DNS is not secure against any on-path attacker. There is no checking or validation. And so for off-path, they would have to guess the ID, which is 16 bits, so it's 1 over 2 to the 16. So they do have to guess, but on-path, since they know the packets, they can just poison your cache. And another attack is called Kaminsky attack. And this is essentially when you have a query, you query like many non-existent domains to try to beat the race condition from the actual name server and then poison the cache. And this relies on the fact that we also cache additional records. And we can spoof corrupt the additional record, and that will be saved. And this can trick the victim into visiting many domains through HTML tags. And the defense for that is called bailiwick checking, or not for that, but in general, defenses are bailiwick checking, which is we only accept name server records that are in the name server zone. For example, berkeley.edu can only provide record for something.berkeley.edu and not like mit.edu, since Berkeley doesn't have ownership over that domain. Another defense is called source port randomization, which essentially just adds another like a ID of the port, and so the attacker has to guess that thing as well, which is also 16 bits, and that's 2 to the 32, right? So it's 1 over 2 to the 32 for an off-path attacker to guess the probability. Again, this is quite quick, so if you need slower explanation and you want to go in detail, please check the website or lectures. They're quite good. I think Kaminsky can be confusing, uh, just because what we're talking about here is this section called additional, and it's only used for like in between your layers when you want to go to another lower level server to figure out where to go next. And so what happens is that like an HTML tag will have a lot of requests to like fake websites. For example, fake.berkeley.edu, and your browser tries to render it and makes the request to that thing. And every time the fake request cannot be cached since it doesn't exist, right? So you make new requests every time, and every time the attacker has a chance to beat the race condition and guess the number, and so like poison your additional section with whatever they want, essentially. That's kind of the high level of Kaminsky. I recommend maybe checking out more because it is quite confusing at first. Okay, but how do we actually add integrity to DNS, right? Because right now we have essentially no integrity. And this is when we want to add something called DNSSEC. So let's see how that would work. Hmm?
Oh, DNS.
Yeah. Oh, no. Yeah, DNSSEC. We should set up some sort of symmetric key, but then how would we share that key with the name server? And then also we would need a key for every person wanting to access this name server. And if you think about like every single computer making a request like a lot of times a second to name servers, and each of them needing a key for themselves, this would not be scalable to the internet, right? There's no way we can handle that many requests every time. Instead, we use something called digital signatures or asymmetric cryptography. Yes, okay, so signatures would not help us if a name server is malicious altogether. But we also have something called trust delegations and anchors. And we're going to show this in the next slide. But essentially, if we trust one source, let's say the root, then we will trust the root's trust. So if the root tells you, hey, this is my child and I guarantee it's like a legit child, then we just take it as a fact and we just trust the root.
We have to like absolutely secure that.
Yes, this is a great point, actually. That is a good point. And I don't know if the slides are good here, but let's see. Oh, shoot.
Something.
So essentially, like the general thing, well, that's a good question. I'll go back to it in a sec. But the how it works is that if you want the IP, the name server doesn't just give you the children. It says, I don't know the IP itself, but here is my .edu name server, as well as the signature on that name server, and public key, and my public key. So what that means is like uh, there's a signature over the records. So an attacker cannot forge it since the public key of the name server is public, right? So they need to know the private key, and hopefully the private key is not leaked. That's like the assumption. And if we can trust the beginning server, then we can trust everything underneath. And so that's like the high level idea of how DNSSEC will work. Uh, yep. So this is just to show you what it would look like. For example, you now have this something called DNSSEC key, right? You also have RRSig, and that's just a signature on all the records. And then DNS key is the public keys, and DS is like your signer, as in the person who you're trusting, right? And they kind of signing the next records and like passing on that chain of trust. And I think it makes more sense in the diagrams, perhaps. So let's see if we kind of go into issues without really looking at diagram, which is not quite helpful, but it's okay. One thing with DNSSEC is something called non-existent domains. And the problem with that is like when you sign records, that's kind of slow because you're computing like encryption hash thing on top of it, right? So what you do is you pre-compute signatures on like a range of domains that don't exist. So if you query a server like fake.berkeley.edu, it doesn't have to make a new signature and like compute that. It just says, this is the range that doesn't exist, and here's my signature that I've done offline, right? So the NSSEC record says there's no domain between these ranges, as you can see here, between A and B, right? And the DNS doesn't do that because it doesn't need to sign, so it can just tell you, I don't have that domain. And then the problem with this, an attacker can figure out what ranges have like real websites and what ranges do not. Okay, kind of a lot of things taken, kind of to be honest. But the key idea of this thing, of DNSSEC, is that when you want to sign beforehand and delegate trust, you have two things. You have KSK, which is key signing keys. And like the first KSK is like the roots KSK, right? And then ZSK is like the zone signing keys. And these are the keys to sign the next zones. I think it makes sense to just have a look first. And essentially what the idea is that, okay, I trust the root, and then the root gives me the next domains, and then it also signs these domains, right? It signs the domains, and as well as domains, it signs the keys of the domains. So like, then we know it's trusted, and we also trust the key of the child domain, since the server put a signature on that, right? I don't know if you can, let me move this thing for a second. So yes, and you might wonder like, okay, since we're trusting the KSK of the server, like the idea is that how do we know the first key is valid, right? Like, and that thing, the answer for that is just hard coded. So a lot of laptops or like browsers, not sure, they come with a hard coded key for a root domain. So like the first server, we know like it's guaranteed to be true, and it's already like there's like a set of agreements and whatnot, and your laptop just knows the answer for that thing. So since we already trusted the beginning, then whatever this KSK signs in terms of the keys, then we can take a value of trust and we can carry on this chain of trust and make sure it's all valid. Because if you have an attacker, they would need to be approved by each of these servers, right? And the only reason they would be signed over and approved is if like any of these are just compromised. And we just hope that none of the real servers are compromised, because at that point, like, you can't really do much. Yeah. And let's see if there's more clear. Hold up. Also, another thing, they kind of skip over this, but the idea was that you have like one key per server and then they sign everything. But there was an issue in that, is that let's say the org is changing its key, right? And if they change the key, then they would need to tell the root, hey, I changed my key, can you re-sign? And so that would take a lot of work. So we separated the key zones of each like domain server. It's like a KSK and ZSK are like, you can think of as like the top and the bottom. So the KSK gets approved by the root, right? But if the org wants to change its key that it signs the next org, it just changes the bottom key. And since this thing stays constant, the root doesn't have to do anything new. It's the same signature the same way. And this KSK is trusted, but org can change this internal key however it wants. Like, it's pretty efficient, and it can just re-sign the children KSKs, and it's the same thing as before. It's just less computation in terms of keys. Again, this is quite a lot, and we're going through it in a bit of a fast pace, so sorry about that. Sorry? Yeah, we can go through this afterwards in a bit more detailed questions if needed. And then the summary is that DNSSEC is used to add integrity and object security to our DNS responses. And we use trust delegation all the way from trust anchor or root, as well as signatures to verify the validity of a server's response. And the implementation is that on top of responding with children's zones, the NS will add a signature on the children's public keys, which is like the KSK. And then as well as it will return like a record that's signed, basically. Yeah, and then also when providing a final answer, the name server signs the final answer as well. So the whole chain is protected, and no one can just give you at the last step like a fake answer, because they would never get the signature, and we don't trust their keys. That's essentially the idea. And now, how do we protect against network attacks? I'll let Jinhao take over from here.
Yeah, we do have 2 hours, but I think the issue, like when the first TA that creating these slides, is we have 9 different sections. But if we just simply just extend, let's say like 20% more in each section, it will be a lot in total. So yeah, but this is just, I think this review is mostly to give you know like what are the like main topics that's covered in the lectures that's likely to be in the exam. But I think for the detailed thing, you can either ask us or like look at the recordings or like go to the textbook. They do have more examples for each topic. Okay, so now we need to think about how do we protect against attacks. And the reason we still need defenses is like, we do mention a bunch of attacks for all these protocols, but none of these attacks are like perfect. So we do need a way, in this case, to detect when these attacks are happening, and then like maybe like we can do something to like mitigate these attacks. Yeah. So the idea is that we're gonna have detectors. It's gonna depends on like locations we install these detectors, and within each detector we can have like different detection techniques. And yeah, that's the things we're gonna talk about. So we're gonna first go over the detectors. So the first detector is called Network Intrusion Detection System, or NIDS. It's located between the router and the internal network. So it basically can see all the requests to and from outside internet. And therefore, it does have the ability to cover the entire network, just a single NIDS. But the downside is that it cannot like categorize packets. It cannot see the packet. It could see packets out of order because of the nature of the internet. And the TCP connection that reconstructed at NIDS may not match the TCP connection that the end host can see. So for example, if the NIDS escapes or like the host doesn't. Or another example is like, if you still remember the TTL, we mentioned in the lecture that some packet might live longer live long enough for the NIDS to see it, but not enough for the actual endpoint to see it. And if the network is under like TLS or like any kind of encrypted like traffic in NIDS, because it does not have the key to decrypt these packets, so it cannot run any analysis over these packets. A second type of detector is called host-based intrusion detection system. So you can think of it as like installed directly on the end host. For example, if it's like a backend if it's like a backend web server and this thing is installed in this web server specifically. And the nice thing about HIDS is that it can actually check the data has been received and see how data is being parsed. And because it's in the host, and it does actually have the key, and then you can just decrypt the data because yeah. And the downside is like very expensive, and you actually need a lot of like compute resource to run this host-based intrusion detection system, and it also is still susceptible to like a certain type of attack, like path traversal.
Or is it
You mean what system? Like existing systems? Depends on like whether you carry your like a system or not. So let's say if you host your own like personal website on a GCP machine, likely you don't have any of them. Maybe like, okay, so I think Google Cloud, they have some sort of like an IDS, but because think about it, like when you host your own website, you're not gonna have you ever like tried running any host-based intrusion detection system? Do you care about the intrusions? So that depends. Yeah, so it's not necessary, but like I think it's more likely used in industry-based like things. Yeah. And of course, another way, which is I think is slightly different from the previous two categories, logging, where the web servers can actually just generate a bunch of logs with information like what web requests have been made, what file has been accessed, and what application has been running, or like what kind of user has logged in. So these things will be recorded in the persistent storage like disk on the host. And the nice thing is it does have the entire view of the like internet activity. But the downside is that you cannot really have any like real-time detection, because to detect attacks, you actually need to go through the logs and see any like suspicious behavior and run some sort of like pattern matching algorithm to decide. So you can only do this in, let's say, in a batch basis. Let's say you run an analysis every day for the logs in the past 24 hours. Then you can maybe detect some of the intrusion activity, and then you can apply some sort of mitigation. So there's no real-time detection when you're using logging. And for detection techniques, we do have a bunch of them. So for example, like we have a signature-based detection. The idea is that you just look for the activity that matches the structure of a known attack, similar to like blacklisting. And the nice thing is it's very reliable for known attacks. And the downside is that because it's a signature-based, so whenever there's an attack that has like slightly different signature in terms of like attack, then you might not be able to catch these kind of attacks. And the second category is called anomaly-based detection. The idea is that you kind of develop a model of what normal activity like looks like. And then this model will flag any activity that's deviated from the normal activity. And you can think of it more like a whitelisting. So the nice thing is it can catch like attacks that's never seen before. But then the problem is creating this model is kind of tricky, because you do need some like training data to define what is the normal activity. And it might has a very high false positive rate, like just flagging a new like normal activity as an attack. So we also have this specification-based detection. So idea is we manually specify like what's the normal activity going to be look like and flag them. So the difference compared to last time is that in the anomaly base, we use a model to learn what is the normal activity. But now we do have a concrete specification about what's the normal activity going to be look like. So the good side of this is you can actually catch like attacks that's never seen before, and it does have like kind of low false positive rate if normal activity is well defined. And the downside is like is this if condition, like we do need this specification to have a very good definition of normal activity, and it does cost time to like write good specifications. Just think about like the design doc of your project too. It's really hard to write a like perfect design doc. So lastly, we have this behavioral detection. The idea is that we look for evidence of compromise or result of exploit instead of actual exploit. So the good thing about this is it can catch new attacks. It can have like quite low false positive, and it's pretty cheap. But then the problem is it happens like after fact because we are looking for evidence of like a compromise result. For example, if the attacker's goal is to like temper a file, then you can probably detect, okay, the integrity flag of this file is changed, but then this file is destroyed anyway. But then you cannot really, you do need some way to recover it, but that's another story. And attacker in this case, if it knows that you have behavioral detection like deployed, it can actually try to avoid this detection by using a slightly different like behavior to execute the attack. And I think for these different detection techniques, I do recommend to go back to the textbook. We do have like a more concrete examples for each one of them, so it might help you to understand like the difference between them. But I do agree that they have some overlap, so a bit tricky to like distinguish between these categories. Yeah. So another way to running attack in the network is like instead of just like tempering something, you can also disrupt the availability of a service, which is called denial of service or DRS. So the strategy is like we can either exploiting a program flaws, for example, like using a buffer overflow to shut down a service, or we can do like resource exhaustion, like you can just send a lot of requests that can use up all the available memory for a given server, or you can find the bottleneck in the entire like network and try to exhaust the resource of that bottleneck. So for example, on target applications could be like a very high level application running on the host, for example, like a backend web server. You can also like attack networks, like just targeting network protocols that affects the host internet. For example, if the entire campus is like the output point is just a single router, you can just try to attack that router that can shut down the entire like network of the campus. And the last thing we want to mention is that in TLS, we do provide the confidentiality and the integrity. But another thing that's like also very important is the anonymous. So for TLS, the attacker still knows that which party is talking to which party. But now we want another level of security, which we want to like break this link. Then that the attacker cannot know, let's say, if Nick is talking to Reluca, we also want to break this link. And this is done through Tor. So the high level idea of Tor is like you can think of it like wrap the internet packets like onion. So but it stands for like onion router. So onions, they have different layers. Similarly in Tor, we're gonna have like we're gonna see in the next slides about how we wrap the network packet in multiple layers. And the idea is that in Tor is we have an overlay network above the internet and to provide this anonymity. So with this, like if you're using Tor, the assumption is that no individual node can actually tell who you are and who you are talking to. So the high level idea is that let's say Alice wants to set up a connection to Google, and there will be a bunch of like Tor relay nodes in between. We have 9 here in this case. And Alice is going to select a subset of them and set up a connection by using the Tor protocol. So the high level idea, you just talk to the entry node, and then this entry node will like talk to the next one and then go on. And finally, you're going to set up a connection with the google.com. So the high level idea is that from the attacker's view, it knows that Alice is talking to something in the Tor relay nodes, and the entire Tor relay nodes is talking to google.com. So what if you have like another important assumption in Tor is that you do require like more than one users, because if it's just single user in this case, it's pretty clear that it's Alice that's talking to google.com. But once you have more users, and then from the attacker's view, it doesn't have enough information to tell if Alice is talking to google.com or if Alice is talking to someone else. So the only thing you can see is that Alice is talking to someone and someone is talking to Google, but there's no like concrete relationship between these two. And that's the high level idea of tool. Yeah, so once you have like more users, you have more incoming traffic, and for outbound traffic, and it's like really hard for you to tell like which one is like matching to which one. So the attacking tool, if you think of like malicious nodes, can actually work together. So they can determine who you are and what you're connecting to. So the assumption is that if you have two nodes that are colluded, you do require at least 3 Tor nodes to make sure that the entry node cannot just contact the exit node to directly like link the connection. So basically, we do require like if you have n colluded nodes, we do have n+1 requirement to still guarantee the anonymous. So and we also have this correlation attack. And if you see that packets enter and exit at a certain times, and you can still infer that they're like belongs to the same connection. Let's say if you are the only user that's like talk to google.com in the midnight, then it's highly likely it's like sorry, it's if you are the only user that's talking to Tor and at that time Tor is like sending message to google.com, then it's like highly likely you two are in the same connection. But yeah, so that's kind of the correlation attack. And the defense is like just include more nodes and include more users so that there's going to be like lower probability of a malicious node. I don't think this is the right reason for this defense, but the idea is that you just include more nodes and also like include more users so that it becomes more complicated for the attacker to infer this connection from the timing basis. So availability, and you can because Tor doesn't actually guarantee availability, so you can actually like break Tor by using like RC injection, like we mentioned before. So the defense for availability attack is you can use actually obfuscated entry nodes that look like just like normal TLS traffic. Who thinks the answer is B? Who thinks the answer is C? Okay, we have 2 votes. Who think the answer is none of the above?
I don't know.
Okay, the answer is C.
B,
C.
C, okay.
The third one. Yes.
It's, wait, what? C means can pull the server.
Yeah.
It takes it to splits data.
Yes. So like this option. And the reason for the first two, like being wrong. Okay, so for example, this just says attacker can reliably inject packets after connection has been established, right? This just says, okay, now that we have data and SYN, we can just break the handshake, right? But that's just not true because after handshake is complete, they've already exchanged their sequence numbers and whatnot. So the attacker cannot reliably inject since the data being there in the SYN doesn't change anything about the handshake itself. I don't know if that makes sense, but just because you send some data, you're not inherently changing the way handshake is done, right? So after handshake established, you didn't learn anything because you send more data in the SYN. Like you still cannot reliably inject because you still need to guess the sequence numbers from both sides. And again, the off-path attacker can reliably execute RST injection attack. Well, the answer for that is similarly no, because again, you have to guess the numbers, right? The sequence and port and whatnot. So just because you send data in SYN doesn't mean like you now can suddenly guess those numbers, right? So since you still have to guess, you can't reliably execute these attacks, right? Because reliably implies like, yeah, you consistent basis. But this is just simply not true. But the third one is true because by definition of the setup, right, it says server has to accept data in the SYN packet. Like, right? So this is just true because you can just send some data in your SYN and you're sending the data. Like, it's kind of by definition of the question, kind of a thing. But the reasoning for these two, does that make sense? Okay. Okay, let's go to with these two.
What is the same?
Wait.
I don't think we covered that.
And also sync, I feel in general, how would a cookie be a defense against a DOS attack?
So now you're thinking on the right lines. That is kind of like, well, I actually don't know if we ever
I think I've seen this in many
like.
material.
I don't think
I've heard of it.
but I don't know if you guys like actually meant to know this, but which
But you can just think of it like the high level idea is not about like the cookie itself. It's like even if you provide a sync cookie, the server's still gonna check the sync cookie anyway, right? If you think of cookie as some way to like some like proof of like you're like a legit user, not a like a random user. But even in that case, the server still needs to check the cookie, still needs to do some work to see if the cookie is legit or not, right?
So,
And then that still consumes resource. And I feel like that's the reason behind this question that even with this cookie, even if it works, but then it still kind of requires server to do works to prove it. So it doesn't really.
but like the sync cookie is like a certain number of bytes. So like say the proposed here is that they're checking the sync cookie.
Yeah.
Which is like a session token.
Yeah.
And if the session token matches with whatever is in the database,
Mhm.
only then we look at the rest of the payload which they're sending.
Yeah.
So if this is the case, then they're not going to be even affected by the payload.
Oh.
Which is coming in, because they're not even accepting it without checking.
But even checking that takes resource, right?
But like, would that really like?
I think I understand your question, but I think that there's a conceptual thing. I think what they're referring to is, for example, during the handshake, you expect the client side to keep all the metadata of the connection, and the server doesn't care. Like the server doesn't keep an open connection thing waiting for your ACK as a user. Like for example, if let's say attacker has like a million devices, right? And they all send SYNs to the server, and the server opens like some sort of like place in data where they're waiting for your ACK as like a user, right? And if they keep opening it, you're exhausting the server, and then it runs out of space for real users. SYN cookie is the idea that the user stores the connection, not the server, during the handshake. So during the handshake, the user is responsible to collect all the like the handshake responses and send the whole thing back to the server, and then the server can validate, right? So server doesn't keep like an open connection. Like the server does not keep open connection during the handshake, like full data for every user, so it doesn't get exhausted by a lot of SYN flooding. Like I think the conceptual idea is that it protects against like SYN floods. Um, but the question here is saying like, okay, let's say SYN cookies do protect against SYN floods, which they do by definition. I think it's just the word cookie is a bit misleading here. And then they're like, does this provide a valid defense against DOS here? Well, okay, the whole handshake is given to the what's it called? the client, the user, right? But the server accepts your data in the SYN. So even if you remove the metadata handling and give it to the user, the data in the first packet is still accepted by the server, right? So like even if you use the SYN cookie thing to protect against SYN attack, SYN flooding, you still are taking in all the data that they give you by this part, right? So that kind of defeats the point. Because if I can just SYN flood you and give you like bazillion bytes, then I can just like I don't care that like about the next ACK and all that because you already took my data. So the answer here is false. I don't know if like maybe this is more clear. So this is the answer for the first one, and mm, how many lines? Yeah. So this is kind of what I was talking about. Yeah. So I don't know if this makes sense to everyone, but the SYN cookies protect against accumulation of connection metadata due to incomplete three-way handshakes. However, regardless of whether SYN cookies are enabled or not, the server will still have to consume resources to receive data before three-way handshake is complete, making vulnerable to DOS. Do you have any more questions? Does that make sense? Kind of. Do you get the SYN cookie part?
Does SYN cookie provide a valid defense against the proposed DRS attack if Alice did not modify the TLS
Yes.
TCP in this way?
Exactly. And yeah, this is why, like, even with SYN cookie enabling, this fails because the first step still like defeats the whole point by making the server consume data like that they received. Okay, maybe now we can go here. So now Alice uses her modified three-way handshake to form a TCP connection with the server. Assume that some source port randomization is not in use. Yeah, source port randomization is not in use. What fields would an on-path attacker have to guess in order to inject some data from Alice client to the server?
Remember, it's an on-path attacker. You think about what's the capability of an on-path attack.
Just put not a debuff because they're off path, so they'd be able to see everything.
That's exactly right. Is that what you want to say as well?
Yeah.
Okay,
Yeah, say that on record.
exactly. So since they can see packets, they see each of these points, right? So like exactly you said, they don't need to guess any of these because they know what they are. I think that should be the answer. Yes, okay. Yep, that's exactly right. Okay, so see if we can get through as much as we can of this question. A lot of reading in this question, to be honest. It's a lot of reading in this question. Yeah, I think maybe we just go kind of through it. I don't know if you guys had time to even read it, but essentially the idea is that I think this summarizes it well. So you have this kind of diagram, and now you're sending some sort of a token, right? So your token, you send packet with a token request, and then the server receives that and makes like a MAC with its own key, and it responds with SYN-ACK packet to the client containing the token that client sent. And then the client and server both store the token. Then the client responds with an ACK packet as normal in TCP. However, in the like further like future connections, they skip the handshake and they just send the SYN packet with both the tokens that they both like now have, right? And data, same as before, basically, some data. And the server verifies the value of the token, acknowledges both the SYN and the data. The server may begin sending data to the client before receiving the client's ACK as part of the handshake. The server rejects SYN and the data if the token is invalid. So TLDR is just like a just extra token step to then skip the handshake every time. That's the idea, right? And so where am I at? Okay, so if we look at the question, which of the following attacks on TCP becomes more difficult with the addition of token? Do you guys have any idea? What's your reasoning?
They don't have the token, so they can't just like blindly.
Okay, that actually I see the intuition. That's almost correct. But the point of the do you have any other guesses? Okay. So the point of this thing is to essentially speed up the efficiency of handshakes. And the question is like kind of a tricky, but it says like what becomes more difficult with the addition of the token, right? But even if you don't know the token, all you have to do is just guess the correct port stuff at the beginning, and essentially it becomes like a new handshake. So the answer here is actually none of the above, and that is because the token's whole point is that I don't have to always do handshake when I run out of like when for like a certain time frame. It's like a cached handshake, you can think of it that way, right? And so it's merely for efficiency reasons of the handshake. And so none of the attacks become like harder because of the token. Since they can just start a new handshake and they're still guessing the same things they would guess with or without the token. And I think that should be the answer. Yeah, okay, so oops, there's the thing. See if we can finish this question at least. So we have none of the above, and the answer for that is that token is merely intended to speed up the establishment of new connections in the three-way handshake. It makes no security provisions. And yes, that's about right. Okay, let's just go through this part. Major issue with the protocol is that it is vulnerable to replay attacks, as that the adversary can spoof a connection by replaying the token. A potential workaround is to modify the TTL, time to live of the token. Name one benefit and one drawback of using a shorter TTL and longer TTL.
The drawback is that, like, get a short yard, that generate, they would have to initiate a new handshake for, like,
Exactly. Exactly. Yep.
then
Well, you got the first part right. That's exactly spot on. Is that obviously you have to generate new handshake every time, which essentially defeats the point of the token if you put it very short, right? And however, the drawback or not, the benefit is that it's more secure for replay attacks because one token is not valid for a long time. So even if the attacker manages to get hold of that, the connection that you had is already expired, right? So even if you use the token, the server is like, oh, like this is old, like I don't care. I now have a new token. So it just is more secure. Yes, since the window in which yes. So the window for replay attacks becomes shorter because time to live of the token is shorter. So even if that token gets leaked, it doesn't matter because the connection most likely would have ended if it's a shorter TTL. And for the long TTL, it's to increase speed. Yeah, that makes sense. So you don't have to initiate new handshakes every time, right? Okay. Is there more to this question? Okay. I think that's it. Sorry about that. There was a miscommunication with the existence of the worksheet. So we could have easily gotten through this worksheet, to be honest. True. But it's fine. I guess it's more practice. You can